So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today, we have the pleasure of having Xingjian Zhang, and he will tell us about Succinct Perfect Zero knowledge for MIP STAR. So Xingjian, he has given a talk to us before. He is a postdoc at the Computer Science Department, University of Hong Kong. Got his PhD from Tsinghua University under Professor Xiongfeng Ma. And his main interests are in quantum non-locality, quantum communication, and quantum cryptography. Yes, so the floor is yours, Xingjian.
Yeah, thank you. And thank you for the invitation. So it is my pleasure today to introduce our recent results, the Succinct Perfect Zero knowledge for MIP STAR. Yeah, so our work is now on arXiv, and this is a collaborated work with Dr. Hong Haofu, who is now currently an assistant professor at the Concordia University. Yeah, so actually today's talk is more like an in some sense an extended reference, because there are very many concepts that are involved. So I will be more focused on maybe describing the results and just give the high-level picture behind the proof. And if you are interested in the maybe some specific parts of the construction and the proof, then maybe we can schedule a later discussion on to discuss the specific parts. Yeah, so the outline for my talk today will be as this. So first, I will give the background, including two main ingredients. One is the MIP star equals to RE, and another part is the zero knowledge proofs. So this gives the two notions in the title of my talk. And then I will describe our main result. And before going to the proof, I will give a black box outlook. So it is like given the main result, so maybe what can we further do and what we haven't achieved. And finally, I will give a very high-level proof sketch of the results. And before going on, I would like to maybe share with you this link. So this was the recording of a workshop on the discussion of MIP star equals to RE that was held in 2023. So the people did a 1-week workshop. So they divided the entire proof of the MIP star equals to RE into several parts, and there are many concrete topical showing how this proof is actually achieved. So I think this is a very, very helpful introduction of the celebrated result. Okay, so we can get started. So first is about background. So I think the biggest breakthrough in computer science in 2020, or even in the last decade, is the proof of MIP star equals to RE. So this result gives a complete characterization of the connectivity class MIP star, which is the multi-prover interactive proofs, and the provers share entanglement. So entanglement represents the star. So this complexity class is shown to be equal to RE, which is the class of recursive enumerable languages. And we know the complete problem for RE is the halting problem, which means the instances that the Turing machine will halt. And the yes instances of the halting problem can be verified by a Turing machine in finite steps. It is like you just run this algorithm and it will stop after a finite steps. But for the no instance, the Turing machine may never stop. So there is no universal Turing machine that can tell these instances. So the RE complete problem halting is a famous undecidable problem. Okay, so this is about RE. So what about the MIP star? So MIP star at its essence is a nonlocal game. So here I depict a simple two-party nonlocal game. So we have a referee here and two non-communicating nonlocal players. So in the nonlocal game, the referee will send the players questions X and Y, and the players, say Alice and Bob, will give the referee back the answers A and B. Then the referee will check their answers with respect to the questions, and if the answers satisfy a specific relation which they agree on before the game starts, then so here the verifier will use a decider to decide whether their answers are correct. And if the decider gives you the value 1, then the nonlocal players win this game. Now, to transform it into the MIP star protocol, so the referee is now described as a classical verifier. So this verifier will send classical questions and receive classical answers to check if they satisfy the relation. And the verifier has his computation power is bounded. But for the players in this proving system are now the entangled provers, so they share entanglement, and although they do not communicate with each other, their computational capability is all powerful. So they can do very general quantum computation on their own side, and they claim to be able to prove something, and their proof of the statement is now encoded in the winning strategy, is now encoded as the winning condition for this nonlocal game. And then in this interactive proof system, the nonlocal provers might be malicious, which means that although they claim to be able to prove something, actually they may not be doing this job, and they hope to, so they might try to force the verifier that they can do the job. Now, the questions and answers in the nonlocal games corresponds to the interactions in the interactive proofs, and winning the nonlocal game is corresponds to the proof of some statement. Okay, now to encode an instance of the halting problem, the complete problem for RE languages, so whether a given Turing machine halts or not, into this MIP star system, let's consider a sequence of nonlocal games. So the sequence of the nonlocal games requires a growing amount of entanglement to win perfectly. So we are not dealing just one game, so we are dealing with many games, and the games is labeled with a subscript I. So this I corresponds to the size of the nonlocal games. So if the provers claim that a given instance, so now a given instance means the Turing machine will halt at some point. So they claim that it is the case, and they can indeed prove the statement. Then after some game n, then the provers can always win the nonlocal game Gn with a probability higher than a threshold. So here, let's say maybe to win the game perfectly. But if they cannot show the proof, then for every game in this family, so their winning probability is strictly upper bounded away from 1. And this S means the soundness parameter. Now, informally speaking, the proof of the result MIP star equals to RE is to construct such a sequence of nonlocal games where the question lines, the answer lines, and the decider all have a polynomial size, such that the classical verifier can indeed sample the questions and check the answers. So this is basically the idea of the MIP star equals to RE. Okay, before going on, we have a closer look of the MIP star proving system. So it is an interactive proof system. So there is a verifier and some provers, and they interact to do something. Now to see that MIP star equals to RE is really a very powerful result. So what it means? So before the MIP star, there are other interactive proof systems. So originally, the interactive proof was developed for the single prover case, a single classical prover and a classical verifier. So this gives you the IP system. So a celebrated result is that the IP equals to P space. And later on, people generalized the IP into QIP. So in the QIP, the messages can be quantum. So the verifier can also do quantum computation himself. So the quantum computation is BQP, which means that the verification needs to be efficient. but in general, the verifier can do quantum computation. So what might be surprising is that IP equals to QIP. So the quantumness in the single prover system does not make a difference. And another approach is to generalize the IP into MIP. So in this case, the verifier is classical, but now we have multiple provers. So in this multi-prover setting, the things become much different, and it was shown that MIP equals to NEXP. And we believe that NEXP is, so we know that NEXP includes P space, and we believe that there should be a strict separation. And NEXP is strictly included in NEEXP. So here maybe I make a remark. So NEXP is a like NP, but now the P is replaced with EXP. So polynomial replaced with exponential. So NEXP is strictly included in NEEXP, and by this step, so all the languages are decidable languages, but we later know that NEEXP is strictly included in RE because it contains some undecidable problems, and we now know that RE equals to MIP star. So the MIP star is much more powerful than MIP and also IP. Now, the question is, why is this MIP star so powerful? So we may notice that there are two central ingredients. So first is that there is an improvement with multi-provers. So MIP is more powerful than IP. And another thing is that now with this star, with entanglement, the MIP star is strictly more powerful than MIP. But the tricky point here is that why this quantumness only kicks in for a multi-prover system. So because we know that IP equals to QIP. So quantumness does not make a difference in the single prover system. Okay, so for these two questions, so the first one, so the improvement with the multi-prover setting is that in this case, the verifier can cross-check the behavior of the provers. So let's consider maybe the example of proving the three-set instances. So three-set is an NP-complete problem. So in one single prover interactive proof system, now this prover claims to be able to show that a given instance of three-set can be satisfied. So this means that okay, so in general, the three-set can be described as a constraint system. So in the constraint system, we have many variables and many constraints. And for each constraint, there is for each constraint, it means that a subset of the variables need to satisfy a specific function. And now we have many constraints. And the satisfying assignment means that you can assign the values to all these variables, and this assignment satisfy all the set of the constraints. Okay, so now the prover claims that she has an assignment to this constraint system. Now, how the verifier checks this proof? So essentially, to some sense, the verifier needs to ask this single prover all the questions. So all the questions in this constraint system. So this is not very efficient. But in the case of two provers, let's say maybe this setting. So in the two prover system, let's consider the MIP case. So in this MIP case, the provers share randomness and they do local operations. Then in this system, the verifier can ask the provers questions in a more clever way, which is that the verifier can cross-check, which means that, for example, the verifier asks at least one prover a constraint and asks Alice to give a satisfying assignment to this constraint. But for Bob, the verifier asks one variable within that constraint and just like Bob to give an assignment to this variable. And then the verifier checks the consistency between the assignment on this variable between the two provers. So in this way, the questions can be sampled more efficiently, which gives this gives the verifier more power in this proving system. So this is the improvement to the multi-prover setting. And now let's see why when we boost MIP to MIP star, the entanglement make a difference. So something that is missing in the classical case is that when you have entanglement, you can do something that is called self-testing. So self-testing basically means that the verifier can simply ask some classical questions and receive classical answers. And these classical commands can check the quantum behavior of the provers. So this is something that only shows up in the quantum setting, and it is also only doable when you consider multi-provers. So it is not something possible in a single party setting. So this, in some sense, explains why we have MIP equals to QIP. And also because of the self-testing, it was shown that QMIP, so QMIP means that the verifier has the efficient quantum commutation power, and the interactions can be quantum questions and quantum answers. This QMIP actually equals to MIP star. So the verifier can be restricted to purely classical commutation. Now let's see what it means by a self-testing. So self-testing means that the verifier can check the behavior of the nonlocal provers uniquely. So let's consider, for example, the CHSH game. So in the CHSH game, the questions and answers are all binary, so they take binary values. And the winning condition in this nonlocal game is that the XOR of the answers A and B equals to the product of XY. So this is the winning condition. Now so as you are familiar with, the maximal value that the quantum players can achieve in this nonlocal game is 2 plus square root of 2 over 4, so which is approximately 85%. If the players achieve this winning probability, then the verifier can be certain that the provers indeed share a maximally entangled state, and Alice must be mirroring X and Z, the poly X and poly Z, and on both sides he must mirror these observables X plus Z and X minus Z. And also, this self-testing result has some rigidity properties, which means that it can be made robust. So if the winning probability is epsilon close to 85%, then the verifier can be certain that the fidelity in the state shared by the provers in this case is also very close to the maximally entangled state. So the self-testing has robustness guarantees. So here I make a conclusion. So the self-testing properties is that the verifier can do rigid classical commands to check the quantum behaviors of the provers. And also the questions can be actually very short. So for example, the verifier hopes to check that the provers share n pairs of the EPRs. So of course you can do n CHSH separately and check that the provers have the n EPRs. But the questions in this case is kind of lengthy because you need to sample the questions for n instances separately. But actually you do not need to do that. You can do a so-called parallel self-testing and ask the questions in a smarter way, and the NEPRs can be robust self-tested by log n questions. So you do not need to send the questions independently. You can make a joint question to check the NEPRs together. So the self-testing is a purely quantum technique, and this allows for something that is called a recursive question compression. So this technique was proposed in 2019 by Natarajan and Wright. So roughly speaking, it means that originally you have a family of nonlocal games, this GI, each with question length Qn. So this n means this I, the subscript of the game. And the question length can be lengthy, but after you do this compression, so compression essentially use the parallel self-testing. After compression, there is a outputs another family of nonlocal games. In this nonlocal games, the question length becomes exponentially shorter, so the question length now become polylog in Qn. And the question reduction basically keeps other parameters of the nonlocal games almost the same. So by saying almost, I mean that there is actually some tricky thing, and I will mention them later. So in this way, you can reduce the length of the questions. And so this makes the MIP star much more powerful than MIP. Okay, now after discussing what the interactive proof system can solve, so what kind of problem, the computational problem they can solve, so whether classical or quantum, a single proof setting or multi-proof setting, let's now take another perspective of the interactive proof systems. So originally, one motivation for the study of interactive proofs is that they allow something called a zero-knowledge proof. So it means that the prover, if the prover can really do something, they can prove this mere fact that they are capable to the verifier and convince the verifier that they have the capabilities, but not showing anything how they do the job. And mathematically, this is formalized via the simulation model. So now let's consider this interactive proof system where the prover and the verifier have access to the input, so an instance, and the prover wants to prove that this instance belongs to some language L. So for example, say NP language. And suppose the prover indeed has the proof for this statement. Now, in the Euro interactive proofs, the verifier may also have access to the so the verifier has access to the input, and they may use some additional input on their set, which we denote as Z, and interacts with the prover. So this is the Euro interactive proof system, and maybe the prover needs to show the verifier how they do the job. But now let's consider another perspective, another case. So in another case, we have a so-called probabilistic polynomial time algorithm, so a PPT algorithm. So this is called a simulator. And this simulator, upon receiving the input, so this input, the question input and this Z, so these are the only information that are generated by the verifier. So this simulator sample the same, simulator in somehow can sample the same distribution as the interactions. So the interactions means the dialogue, the question and answers in the original interactive system. So the simulator samples the same distribution as the interactions that were in the original proof system. So we notice that this simulator knows nothing about how this proof works. It only has the same knowledge as the verifier, but the simulator just gives you the same distribution that the prover may give to you. So from the verifier's perspective, there is no way for him to distinguish the two cases. Hence, the prover can prove the statement to the verifier without showing the knowledge about it. And the above description is about the perfect zero knowledge. So the viewpoint of the verifier in these two cases are exactly the same distribution. And we can also discuss statistical zero knowledge, SZK, which means that these two distributions are statistically close. And also we can talk about computational zero knowledge, which means that there does not exist a PPT distinguisher. So a distinguisher is another algorithm. So the PPT distinguisher cannot distinguish the two distributions in a polynomial time. And in general, when we talk about zero knowledge, we also consider a dishonest verifier. So the dishonest verifier may deviate from the things that he should do in the interactive proof system, and maybe ask some malicious questions to try to get the knowledge of how this proof works. And we can so in general we should consider a dishonest verifier and talk about zero knowledge. Okay, the results about the zero knowledge of these interactive systems are as follows. So people have shown that the single prover, the IP system, equals to computational zero knowledge if you assume that one-way function exists. But because of some evidence, people believe that it is not the case that IP equals to SZK, statistical zero knowledge, and perfect zero knowledge. So these are some results that are unlikely to be true. But for the case of multi-prover, then things become much different. So we have the result that MIP equals to perfect zero knowledge MIP, which means that every multi-prover interactive system can be augmented to a perfect zero knowledge version. So we do not assume any intractable computation assumptions. And furthermore, we also have that MIP star equals to perfect zero knowledge MIP star. So this includes several results. So the first result shows that the perfect zero knowledge MIP star includes the complexity class of NEXP, which means that you can prove every yes instance of the NEXP in the perfect zero knowledge MIP star protocol. So note that NEXP equals to MIP. So everything that can be done in the MIP system can also be done in the perfect zero knowledge MIP star system. In this construction, the MIP star system includes two provers, so just Alice and Bob, and the number of interactions between the provers and the verifier takes polynomial number of rounds. And later, people also show the construction of MIP star equals to perfect zero knowledge MIP star, which means that every MIP star system can be boosted to a perfect zero knowledge one. And in the first construction, the result relies on 6 provers, so not just Alice and Bob. But the good news is that they only need to take one round interaction with the verifier to show that they have the proof. And finally, the previous state-of-the-art result is that MIP star equals to perfect zero knowledge MIP star. So in this case, we only have 2 provers. So just Alice and Bob can do the job. And Alice and Bob just need to take one round of interaction with the verifier to show that they are capable of proving this statement. So the key point for this latest result is that when Mastel and Slofstra show the proof, they already have the knowledge that MIP star equals to RE. So we have this result for the proof. So because we know that MIP star equals to RE, we know the complete problem for the MIP star class, so which is the halting problem. Now you can use the zero knowledge proof for the halting problem to construct the perfect zero knowledge version for the MIP star. Okay, so by this step, so everything seems very, very well, but there is still something that can be improved. So now I compare the previous result and also our result. So the first column is the results that can be achieved for perfect zero knowledge MIP. So the classical case, the number of provers is minimal, which is 2, and the number of interaction is also minimal, which is 1. And we have the constant completeness and soundness. So basically, it means that if they can do the proof, then they can win the nonlocal game with probability 1. And if they cannot do the job, then the winning probability for every instance of the nonlocal game is strictly upper bounded by a constant. So every instance, no matter how large the game is, the winning probability is always a constant. And the question can be very short. So the question length is just logarithm in terms of the parameter n. And the answer length can be a constant. So you just the provers just give back constant length answers. So this is the result for the classical case. And the previous perfect zero knowledge MIP star is given by these parameters. So the number of provers, the number of interaction round, and the completeness soundness are all optimal. But the question lengths are much longer than the classical case. So it takes polynomial question length, and also the answer length is also polynomial. So this is something we prove in our work. So we prove that the question length can be improved to a polylog with constant answer, or you can also construct another perfect zero knowledge MIP star protocol with constant question length and polynomial answer length. So these parameters are very close to the optimal result in the classical case. And before going on, I will so here I give a black box outlook of the.
Sorry, Xingjian. Could you go back to the previous one? I need give me a little bit of time to digest this table. Okay, yeah, sorry. So you said your result is almost optimal compared to the classical correspondence?
Yes.
Okay.
But maybe with a little bit different because the classical case people can have log question, but we only can achieve polylog at this moment.
Okay. Okay. No, it's equally fine to me.
Yeah, but yeah. So maybe in the next slide, I will discuss what this improvement will indicate.
Okay. And the previous results, this is by 2024 result by Slofstra. Okay.
Yeah.
Okay. Good.
By this result.
I see.
Yeah.
Okay.
So so the three reference corresponds to these three results respectively.
Okay. Good. Thank you.
Yeah. Thank you. Okay. So maybe we can have a black box discussion of our result.
Can I just have a quick question, just out of curiosity? So, like in your result, you can switch the sort of like which one you want to be constant, right?
Yes, but these are two different protocols.
Oh, okay, yeah, that was my question. Like whether sort of like was it like a one implied the other, or like totally different techniques? Okay.
Yeah. So so there are some difference. There is some difference in the construction, but the total communication cost is polylog.
All right. Okay.
Yeah. Any further question on this slide?
Should be good. Yeah.
Okay. Yeah. Maybe I can go to this slide. Yeah. So so the first remark I would like to make is about the protocol with constant question length and polylog answer length. So this corresponds to the complexity class of AM star 2. So this star also refers to entanglement, and 2 means two provers, and AM means that it is a free game. So a free nonlocal game means that the questions to Alice and the questions to Bob are sampled independently. So there is no correlation in the question distribution. And our results shows that for such protocols, you can actually achieve a perfect zero knowledge version. So the equivalence between AM star 2 and MIP star and RE was a result shown by Natarajan and Tina Zhang. So it is also a very recent result, and now we improved the result into a perfect zero knowledge version. And another thing is about the communication lower bound for MIP star. So also in the work by Natarajan and Tina Zhang, they show that the communication lower bound, the question length plus answer length, it has a lower bound of log. So this is something they prove. And they also construct a zero gap MIP star protocol. So zero gap means that so in the previous slide, we have the constant completeness and completeness soundness. But in the protocol, the soundness is also a function dependent in n, and the gap gradually converges to 0. And they construct a zero knowledge MIP star protocol, which has constant question length, and the answer length is almost log, so up to a log star. So it is, I think there are three log in this coefficient. So it is very close to this lower bound. But we didn't succeed in making a perfect zero knowledge version for the MIP star protocol. So if we have a perfect zero knowledge MIP star protocol so maybe let's say maybe not for RE, let's say maybe just for QMA complete languages, then in this sense we kind of show the we will kind of prove the game version of the quantum PCP conjecture. So if we can construct a protocol with just log communication, the question length plus answer length. And finally, something I didn't show in the slide is that about the verification time. So because that when you do the interactive proofs, the verifier need to sample some questions, so there is some sampling capacity. And after receiving the answers, the verifier also need to check the answers to verify the answers. So there is a verification capacity. So when we talk about the succinct proofs, so especially for the IP system, for the zero knowledge proof for NP languages, the most desirable statement should be that the verification time is also polylog. So not polynomial time verification, but be polylog verification. But in the things are not entirely the same for the multi-probe system. So for the zero knowledge, for the succinct zero knowledge, so when we say succinct, we just mean the communication cost is succinct. The verification time must be polynomial, and we show that this is necessary. So the very rough idea is that the verifier needs to read the answer, and this answer is and reading all the messages take a polynomial time. So this is something necessary for the MIP star case. So this is something that can be different from the zero knowledge interactive proof. Okay, so yeah, maybe I will go into the proof sketch. Maybe any question at this point? Yeah, okay, maybe then I will give a very high-level idea of how this proof works. So remember that how we encode the halting, the instance of the halting problem into the MIP star. So originally we have a sequence of nonlocal games. If the provers can show that the Turing machine indeed halts at some point, then by some game they will win it perfectly, and otherwise their winning probability is strictly upper bounded. And the question as the answer length, everything grows gradually grows. But the thing for the verifier is that the verifier's computational capability is very restricted. So he can only do the classical commutation, and he can only do it for the polynomial time commutation. So for the verifiers, the original game construction, the question length can be too lengthy for him to sample, and the answer length can be too lengthy for him to read. So this is something that the verifier may not be able to do efficiently. So we must develop some tools to reduce the question length and reduce the answer length. Now remember that the provers are very powerful, so we do not restrict their computational capabilities. So a very bold idea here is to for the question reduction, is to let the provers themselves sample the questions. And this is the idea of the introspection games, where Alice samples the original question to her. So the original question is X, and Alice generates the answers for the original game A, and similarly for Bob. So Bob samples this question Y and gives the answer B. Then the prover sends the question they sample and the answers to the verifier, and the verifier checks if the questions and answers give the correct distribution for the original game. So this is something nice, but why would the provers follow the rules? So the provers may not sample anything, so they just do not sample the question anyway, or they may collude with each other and discuss a flawed strategy where the provers determine on some seemingly random questions and let their answers. So maybe for Alice's set, so Alice answers A depends not only on X, but also depend on Y. So in this case, if you are familiar with nonlocal games, then you know that the classical provers can do something that seems to be quantum. So now the verifier need to prohibit the provers from cheating. So for this purpose, we can introduce another game. So another nonlocal game, which is called a rigidity game, to check the behaviors of the provers. So this game includes several nonlocal games. So the so-called poly game, the something game, and the don't pick game. So essentially, the construction is to check that the provers indeed sample the questions and they do not pick the question on the other prover. And with a proper construction, the rigidity games can be very efficient and shoot in the question length. Then by gluing these two games, the introspection game and the rigidity game, we can compress the question length exponentially. And also this question reduction can be repeated recursively. Okay, so I will not introduce how these games are constructed, but I will show what the honest players should do in these two games. So in the introspection game, the honest players should measure a state on this space. So this subspace corresponds to Alice's question, and this corresponds to Bob's questions, and this corresponds to the measurements to be done for the base game, for the original nonlocal game. So the introspection Alice, so Alice will take a computational basis measurement on this space and generates the questions. And by using the questions she sample on this space, she will take the original game measurement on this space to generate the nonlocal game answers. And similarly for Bob, Bob will not disturb this part. So Bob will only disturb this system to generate the questions. And after he samples his questions, he will do the job for the original game on this space. So this space corresponds to the original nonlocal game. And Alice's questions and Bob's questions will be independent. So here are some, here for this space, it is separable state. Ideally, it should be plus state and do the computational basis measurement. And for the base game, so for the base game, which means the original, the very original game, for the measurement on the base game, the strategy should be measuring many EPRs with poly measurements. So this is everything that the honest players should do in the introspection game. For the rigidity game, essentially it is the parallel self-testing of EPRs, and we will do a parallel magic squared self-testing. And in this nonlocal game, essentially they will also measure EPRs with poly measurements. So here I highlight these 2 points, and maybe you can keep it in mind because later we will discuss how to show the zero knowledge properties. So now we have a question reduction protocol. The question has become
could I interrupt?
Yeah.
Yeah. So I remember that in their first draft, right, there's an error in the proof. But I'm kind of curious where the error, how the error is fixed. Which part of the argument that, contains the error and how they fix the errors?
Actually, I don't quite remember in which part there is an error, but I do remember that there is an error in the question reduction part, and they changed the original game construction. So the
original error seems to be in Thomas Wittig's earlier paper. So they kind of used his one of his earlier key lemma in the proof, and it turns out that lemma is wrong. But I forgot how. I mean, in which part of the proof that require his. But it's fine. I mean, this is minor. I'm just curious. You can continue. Yeah.
Yeah, I will check this point with my colleague. I just remember that a student of Professor G mentioned the flaw and the subsequent fix on this point. So I will check with him on this point.
Oh, good. Thank you.
Yeah. Okay, so now we have a question reduction protocol, but a caveat in question reduction is the decrease in the soundness gap. So in the original game family, we have a perfect completeness and a constant soundness. So for every game, if the players cannot win the game, then their winning probability is strictly upper bounded. But for the after you do the compression, the soundness becomes something like this. So it is no longer a constant; it is 1 over polylog. So with an increasing n, this soundness will gradually converge to 0. So you will only get a 0 gap MIP star protocol if you do if you just do the question reduction. Now the solution to the problem is to do the parallel repetition. So which means that you play n instances of the base game in parallel. So for example, so this is the base game where you have just 1 question and 1 answer. But now you have a parallel repeated game where the verifier will ask n instances to Alice and Bob, and Alice and Bob will give back the n instant the answers to the n instances simultaneously. the key point for the product repetition is that the probability to win every instance of the nonlocal game, if originally they cannot win perfectly, then the winning probability to win all the instances in the parallel repeat game will decay very, very fast. So the best result for general games, so for a very general nonlocal game, we do not restrict its question distribution or anything. The general case was shown by Henry Yuan in 2016, and he shows that this decay in the winning probability for winning all the instances will shrink at least polynomially fast. So far, we do not know whether this can be done exponentially fast, but at least it can shrink polynomially fast. But if you have games with proper design in the questions and with proper question distribution, we can show that this winning probability will indeed decay exponentially fast. And in our work, we will utilize both results. So we need to use a general case, and we also need a result for the in the exponential decay, which we use the result for projection game. So a projection game means that given if Alice's question and input, question and answer are given, then on Bob's side, for when he gets the question, the correct answer is unique. So this is the definition of projection game, and we will use this exponential decay result. So okay, so now we have successfully reduced the question length exponentially, and the question reduction can be performed recursively for many times. So next we see how to reduce the answer length. So the answer reduction is not something new, and it is actually a purely classical process. So it dates back to the very original result of showing that you can use IP to prove the NP languages. So the answer reduction utilizes the celebrated result, the probabilistic checkable proofs (PCP). So in the PCP, upon given the input, the verifier will use a PPT algorithm V to generate I and D. So this D means the verification circuit, and this I means some positions of queries. So the verifier will just query the proof on some point positions to check the proof. Now the provers will encode the proof into something longer, but the encoded proof is designed in a smart way such that if you just check a constant number of the queries, then you can show that the proof is correct or not. Then completeness means that if the input is indeed belonging to some language, then there exists a correct proof, and the probability of the verifier accepting this proof will be 1. So if there is indeed a proof, then the verifier can accept it. And soundness means that if the input does not belong to the language, there is no such proof, then for every proof oracle, the probability of the verifier accepting the proof will be upper bounded by some soundness parameter. Remember that in the PCP construction, the number of queries can be made a constant. So in this way, the answer length can also be reduced exponentially. But actually, the choice of the PCP is also very important in the construction of the MIP star protocol. And we actually cannot just use a black box construction of the PCP, and we indeed look into how the PCP is constructed to prove our result. Okay, but a problem in answer reduction for the MIP star is that to calculate the complete PCP proof, remember that this proof is now generated by Alice and Bob. So you must use answers from both Alice and Bob to construct this proof, but this is not the case in the original nonlocal game. Now the solution to this point is to modify the original game into an oracularized version. So let's consider this original nonlocal game with the Euro Alice and Euro Bob. Alice gets questions X and Bob gets question Y. They generate answers A and B. Now in the oracularized version of the game, one prover is randomly chosen to be the oracularized player. So for example, the original Alice now gets a role called Oracle. The oracle player will get the original questions, both X and Y, and she is asked to give the answers A and B together. Another prover in the original game will be randomly assigned with a role, so maybe oracle, maybe the Euro Alice, or maybe the Euro Bob, and the verifier will he will give the he will get the question and give the detailed answer. So the verifier will check if the oracularized prover entire answer, so she can generate the entire answer in the original game. If this answer is consistent with the prover generated by the other player. The next thing is that for the oracularized prover, she is able to calculate the complete PCP proof because she now gets the entire answer for the original game. Okay, so now we have all the ingredients for showing MIP star equals to RE, and now we can come to our result. So our first result is that all these 4 steps preserve the original zero knowledge properties for the initial MIP star protocol. So okay, so maybe I will take a recall of the definition of perfect zero knowledge in the MIP star. So it means that for an input belonging to RE, then there exists a perfect strategy. So the players will measure, the provers will measure some entangled state psi with some measurements M and N, and then they will generate the answers to the verifier. And this distribution can be efficiently sampled by some PPT algorithm simulator. Okay, let's see how the 4 steps preserve the zero knowledge properties. So suppose you have an initial MIP star which you already show to be perfect zero knowledge. Then after you do the question reduction, so remember that the question reduction, it is essentially to measure some poly measurements on EPRs. So these are some Clifford operations. So for this sampling, you can have the Gauss-Mann-Neel theorem and do an efficient classical simulation. So for the question reduction, the zero knowledge proof will remain. So in this way you construct a PPT or efficient simulator. And for answer reduction, the things you will do in the answer reduction is to sample so the provers will sample the original answers, and then the oracularized player will do the PCP, and afterwards the verifier will do the answer query. And we investigate the PCP in the construction and found that for the honest provers, the PCP proof can be efficiently calculated, which means that it is not something too difficult for the provers to generate this PCP proof. And this means that it is just a classical post-processing of the original answers. So in this way, you can construct a classical simulator to simulate the distribution in the answer reduction part. And also, there are 2 other ingredients, so one is parallel repetition and another is oracularization. So for these 2 parts, the zero knowledge proof is also not very difficult. So for the parallel repetition, it is basically for the honest players, for the honest provers, if they can win every base game, then they can use the same strategy to win the parallel repeated nonlocal game. And in the parallel repetition, we just need to repeat the game for polynomial times. So it is also consistent with the requirement by an efficient simulator. So because it is only polynomial times. So if the original game can be made perfect zero knowledge, then for the parallel repeated game, it can also be made perfect zero knowledge. And finally, the regularization is just to reassign the roles of the nonlocal players. And so this is just a classical post-processing of the distribution, so which can also be simulated efficiently. So this is the first result. We have the perfect zero knowledge MIP star. And the second result is that we have a succinct perfect zero knowledge MIP star protocol. And our starting point for this construction is that in Mastel and Slofstra's results, they have already constructed a perfect zero knowledge MIP star protocol, which has these properties. So originally they have the constant soundness. So the first subscript is the completeness parameter. The second is the soundness, and this is question length, and this is answer length. So in their proof, they have the perfect completeness and constant soundness. But for some technical reasons, we need to modify their protocol a little bit. And the soundness will shrink to 1 minus 1 over poly. So it is not constant soundness. But we first will do a parallel repetition. And in this way, we can boost the soundness back to a constant. So this is the first step. The second step is on this protocol. So we have a zero knowledge. So in the following, I omit the perfect zero knowledge because we have shown how to construct perfect zero knowledge in the last slide. The second step is to apply the question reduction. So after question reduction, we can reduce the question length from poly to polylog. And finally, we will do a recursive answer reduction. So with a new answer reduction technique, we do it recursively, and finally we can reduce the answer length to a constant. And now you can also change these two steps. So if you can do a recursive question reduction and just one step of the answer reduction, and then you can get this protocol. So the question length is constant and the answer length is polylog. What I do not show in this result is the sampling time and the verification time, but actually they are very important in giving the final result. Okay, so that's all for my talk, and thank you.
Right. Thank you very much for a very wonderful and illuminating talk. So we have a few more minutes. Okay, or guess we can have some questions from the audience. So if you have questions, please feel free to just mute yourself and ask.
So I'm curious about the implication. What can be extend from your zero knowledge proof MIP star protocols?
Mm-hmm.
Are there further applications? Yeah.
You mean maybe some real life applications?
No, I'm not talking about real world application. I'm talking about so are there any unsolved complexity questions that would related to this this zero knowledge MIP star?
I see. I think at this moment, Honghao and I are interested in this question. So because as this slide shows, the question length and the answer, so the question length plus the answer length in our construction is polylog. So we found that if you use the current construction, you can only make one parameter to be. So it is like you cannot do both to reduce something like maybe both to be constant, and this is something that violates the lower bound. But we cannot either to improve them into log or maybe log up to a log star. But the thing here is that we are doing things with the RE languages. So we are doing the construction still remaining MIP star equals to RE. But maybe we can consider a more restricted complexity class. So maybe let's say maybe we just show the construction for QMAA complete languages. So QMAA is much smaller than RE. In the classical case, we have some experiences, something like let's say maybe if you want to do the zero knowledge interactive proof for NP, then things are kind of complicated. But you can also consider the case like you do the zero knowledge for the language P. So P is much smaller than NP. And for the construction of P, we know how to make things very short. So it is much more efficient than the general zero knowledge proof for NP. So from this intuition, we think that if we consider some more restricted complexity class and build a perfect zero knowledge protocol, MIP star protocol for these restricted classes, then maybe we can get better parameters. And maybe the most interesting thing here is to show the perfect zero knowledge MIP star protocol for QMA complete language. And if you can achieve a log communication cost, then we kind of prove the game version of quantum PCP.
So can you give me a rough idea of what is the game versions of quantum PCP?
So maybe you can basically think of it as you have a perfect zero knowledge MIP star protocol for the QMA complete language, and the question length plus answer length is log. So basically, this is the thing you need to do for this quantum PCP.
Okay. So you need to go from polylog to log.
Yes.
Okay. I see.
Yeah, and I think the current bottleneck is about the question reduction part.
Okay.
Any other questions? I have a question that's maybe sort of like not totally related. It's just that like so I've seen that so when they present these results like on MIP star, so normally like you have some previous results establishing with like lots of provers, and it seems like eventually it goes to 2 provers at some point.
Yes.
I don't know if like if it's true that most of the recent results will go with those 2. I'm just curious, like, so because you were giving the intuition that in some sense, so why is this strong is coming from this self-testing, right? Sort of like why there's an advantage for having more provers. But if everything reduces to just 2 provers, then it's telling me that I only ever need self-testing for bipartite entanglement.
Yes.
But there's no gain from multipartite entanglement self-testing. Okay, just feels surprising. That
it is like because we are just interested in the big O notation. So it is like n to the 3 and n to the 2. We do not care this difference. But indeed, if you consider the small differences, then things can be different.
Okay.
Yeah, and also for this improvement, so actually, if you do not care about perfect zero knowledge, then so originally people have already known that 6 prover and 2 provers do not make a difference. But so here the thing is that so people want to do the perfect zero knowledge for MIP star, and at this point, we do not know the MIP star equals to RE. So it is like you just try to boost every MIP star protocol into some perfect zero knowledge version. And the idea here is kind of like to separate the circuit for the MIP star into different parts. And in some sense, it is like to disguise your knowledge in one part from another part. And this construction requires many provers. Yeah, but later, because we know MIP star equals to RE, then it is like you just need to show how to construct a zero knowledge protocol for the complete problem, so which is halting. So it is like the things you do for the zero knowledge for NP languages, because for NP languages we know the complete problem to be the 3-set. So you just need to develop a zero knowledge protocol for the 3-set problem, and here it is similar. So for this problem, we know that how to do it with 2 provers.
Okay, I see. So yeah, knowing that actually helped with the reduction. Yes.
Yes.
Okay. Thank you. Yeah. Yeah. So yeah. Anybody else with questions?
I have a question. In the single prover case, there is a cryptographic application of zero knowledge proof, right? But I'm not familiar with multi-prover zero knowledge proof. But do you have some cryptographic application even in the classical setting?
You mean maybe for this setting?
Yes. For example.
Yeah, I think the original motivation for this result is that people want to remove the intractable assumptions, so such as the assumption with one-way functions. I'm not an expert in the classical case, but I know that this result helps the construction with succinct, the non-interactive the succinct non-interactive zero knowledge proofs. Yeah, because in the non-interactive zero knowledge proof, the Euro construction relies on the random oracle. So random oracle is not something very standard in the in the cryptography. But I know there is a construction that's so it first starts from this MIP equals to perfect zero knowledge MIP. Does not rely on any crypto assumption. And then starting from this point, there is a construction of a non-interactive, succinct non-interactive zero knowledge proof, which relies on the ring LWE. So ring LWE is something that people think to be more standard than the random oracle. Yeah, so I think there are some implications for the construction of crypto protocols relying on more standard assumptions.
Okay, thank you very much. I understand.
Yeah, thank you.
Yeah, I think Taika raised an interesting question because right now we have a few people working on quantum crypto related problems like kind of like reduction between different primitives. And also one of the question is that normally in those primitives, that assumption of one-way function is there. So if we could come up with different assumption and embed this kind of complexity, computational complexity class into the question, that would be interesting. And I think Tomoyuki also suggests Jero to read similar material. Yeah.
Yeah, I can. Yeah, I know the reference for the does this question the reference of the construction with the ring LWE. So maybe I can later send this reference via email.
Okay, thank you.